Hi folks, I wanted to talk to you a little bit more about problem number 70 here. I just want to see if I could do a little bit better job explaining the plus and minus signs here. So again, in this problem, if you pay attention, this particle starts right here at what I call position 1. And its velocity at that point, given in the problem, is 8 meters per second, kind of down and left. So, you know, what you got to remember is that there's a couple different types of physics that's going on here. One type is the free bodies and the Newton's second law equations, and then another type is the study of motion. So when we go through this problem, if we draw a free body at kind of an arbitrary location, a free body might look something like this, where we have the object, the mg is down, normal force this direction, and that's pretty well it. And now the MA vectors look like this. We got the tangential acceleration in this direction, the centripetal towards the center of curvature. So when we write our Newton's second law equations for this problem, sum of all forces in the x direction equals MA, calling this way the positive x direction in the tangential direction. So that's going to be mg sine theta equals ma. And it's important to note that that a is the tangential acceleration. Now, when we sum forces in the direction of the normal, right, sum of all forces in the, I could call it the y direction or the n direction, I guess I'll call it the y direction, that's going to equal ma. That acceleration is the centripetal acceleration, right, due to the fact that the velocity vector is changing direction. So the normal is in that direction, and the component of the mg that's parallel to the normal would be mg cosine theta, minus, because the vector component of this mg that's parallel to the normal points down and right. And then equals, right now, the centripetal part. Since centripetal acceleration is v squared over r, this equation, you know, can be written on the right-hand side, mv squared over r. So the normal is therefore equal to mg cosine theta plus mv squared over r. Now, this theta that I have chosen is in fact this theta right here. And the normal now I can get as a function of theta, provided that I know the v. So what I'm going to do here is circle this equation here and just store it up here and get rid of some of this other stuff. Oh, where'd my eraser go? I don't remember. Alright, we'll just do this. All right. We'll move this up here as well. Okay. All right, now let's take a look at our equation of motion here for the tangential direction. When the mass divides out, and what we end up with is that the tangential acceleration equals g sine theta. All right. Now, from here now is where we move to a different set of physics, where now we're going to be studying just the motion of this particle now. So if we study purely just the motion, the free bodies in the Newton's second law equations are not needed right now. And also we do not need to have the same choice of coordinates. So now I'm going to point here now. This variable s, the way I have this drawn, is defined to be 0 at this location with basically this way positive. And my positive theta is defined in a similar sense, where I've got counterclockwise positive. This acceleration that we found, if you look at the free body, points down and left. So that acceleration is in the opposite direction of what I've called positive for the position vector s. So if I am to use the position s to represent basically the distance up the incline, then s dot represents the speed of this. Now when s dot is positive, it means it's moving up and to the right basically, or theta is increasing. S dot negative would mean it's moving down and left. And then s double dot would represent the acceleration of this particle, which is d squared s dt squared. Or another way to write that, we could say that's equal to dv dt. Now, it's important to note here that this acceleration is in the opposite direction of how we're defining these variables, and that's where the minus sign comes in. So when we relate this dv dt to this acceleration right here, dv dt is equal to minus g sine theta. So now the next step would be to apply chain rule differentiation. This dv dt can be written dv ds dt, which is v. I'm just going to write v because I'm running out of room. So that's going to equal minus g sine theta. And the ds can be written r d theta, and that's coming from the definition of the radian. So this equation now can now be written, let's see, we got v dv equals minus g sine theta times r d theta. I think what I'm going to do here is pause this for a moment and clean up these pictures and get myself some room before finishing this, so just stand by.